Today is video lecture 1. We're going to be going over vectors, coordinate systems, and frames. These are some of the basic mathematical constructs you need to be familiar with before we dive into the real physics. So first let's start off with, the notion of a vector. So a vector is a quantity with both direction and magnitude. You can imagine it as an arrow with some length pointing in some direction. And we can contrast vectors with scalars, which are just real numbers with only magnitude. So for example, if I have the number, 23, that's a scalar. Whereas if I have an arrow that points from 0, 0 to 0, 23, then that is a vector because it's got both direction, it's pointing straight up, and it's got magnitude, it's got a length of 23. And often what we can do is we can express vectors in terms of unit vectors. And now what a unit vector is it's a vector with length 1 that points in a set direction. So there are multiple conventions for unit vectors. Unit vectors are usually orthogonal, which means that they're perpendicular to each other. For example, you can have a set of unit vectors that point in the x, y, and z directions respectively. So you can create vectors from the sum of the x unit vector, y unit vector, and z unit vector that collectively cover all three-dimensional space. Vectors don't necessarily have a set origin. Usually we can take the origin to be the origin of 0, 0, but we can translate them basically everywhere around in space. Now this is how we notate vectors in Cartesian coordinates. You can see some fairly scary notation that took me way too long to make in LaTeX. Cartesian coordinates means that we have real three-dimensional space, right? And let's say we want to go to some specific point. To know the location of each point, we assign each point in three-dimensional space a set of 3 coordinates, x, y, and z, that tell us, the location of the point on the x-axis from the origin, on the y-axis from the origin, and on the z-axis from the origin. And as you probably know from your geometry class, all these axes are perpendicular to each other. You probably know what this three-dimensional graph looks like. Let's say we wanted to do vectors in 2 dimensions. We can just lop off the z element and deal with only x and y. Now, if you look at the first line here, this is how I will usually typeset vectors in my lectures. And this is how you will usually find vectors typeset in textbooks or in other texts. So a vector is denoted by boldface, whereas scalars are denoted by standard type. And so we have the vector v, and we say that that's equal to some scalar x times I hat, and I hat is bold, so it's a vector, and this is a unit vector that points in the x direction. So we're saying that the x component of the vector v, which tells us how far in the x direction we have to go, has a scalar value of x. So that means that we're going a distance x in the x direction. And the way we say x direction is with that I hat unit vector, which has a length of 1. So because it has a length of 1, we know that the length of the x component is x, because x times 1 is x. And we have the same thing with the y and z components. We have y times j hat. J hat is the y direction unit vector. And this means that we're going y in the y direction, a distance of y in the y direction. And we're going a distance of z in the z direction because k hat is the z direction's unit vector. Now, if you were to handwrite vectors, then obviously it's very difficult to bold your handwriting. So what we usually do is we put an arrow on top of the symbol to designate that it's a vector. So as we see here, v is still a vector, it's got the arrow on top, and we leave the hats on the unit vectors and we don't bother putting an arrow because it's very clear that they're the unit vectors. So again, v has a component of x in the x direction, means we go x in the x direction if we were to be walking out along the arrow. We have a component of y in the y direction and z in the z direction. So kind of going back to the conception of the vector as an arrow, I apologize that I don't have a very good graphic for this, but if you think about the arrow, then let's say we want to start at the origin and then go to where the arrow is pointing to. If the arrow is represented by the vector v, then we walk x in the x direction, y in the y direction, and z in the z direction to get to the end of the arrow from the origin, which is the point 0, 0, 0. And now we have polar coordinates. Again, this is something you should be familiar with from your geometry class, but I've included a handy graphic here. So in polar coordinates, unlike Cartesian coordinates, only apply to 2 dimensions. You need to generalize it to either spherical or cylindrical coordinates to describe 3-dimensional space, but that is beyond the scope of this course. Yeah, the scope of this course. And yeah, so as you see on the left, we designate each point with a distance r, which tells us how far away the point is from the origin, and an angle theta, which tells us, the angle between the x-axis, quote unquote, the standard x-axis you'd see in the Cartesian plane, and with the ray that connects the origin to our point. So a theta of 90 degrees, for example, would mean that our point was in the y direction, and a theta of 270 degrees would mean our point would be, in the negative y direction underneath the origin. And here we show how to show a vector r. R is what we're going to traditionally use to signify the position vector later on in this course. So we write r as, using the Cartesian unit vectors, I hat times the scalar r, which is the distance from the origin. Make sure not to confuse the vectors r and the scalar r. So I hat times r cosine theta. As you know from your trigonometry class, r cosine theta is the horizontal distance. You can imagine your unit circle, and the horizontal distance is r cosine theta, where r is 1 in your unit circle, or just r in our case with the polar coordinates. And the distance in the y direction is r sine theta, again from your trigonometry class. And yeah, I mean, the I hat and j hat unit vectors are once again just giving us that direction. I hat is the x direction, j hat is the y direction. And like I said earlier, there's no need to necessarily stick with the I hat, j hat, k hat unit vectors to describe our vectors. We can define new unit vectors that are somewhat more suited to polar coordinates in terms of I hat, j hat, and k hat. We can't really invent unit vectors out of nowhere without being confusing. So what I've done here is, if you look at the second line, I've defined a new unit vector. This is called r hat. And don't confuse this with the vector r. R hat, the hat on top indicates that it's a unit vector. It's got a length of 1. And this just tells us in which direction we're pointing. So r hat is equal to I hat cosine theta plus j hat sine theta. And if you look at the definition of r, we can see that the vector r is equal to just the scalar r times r hat, which kind of confirms our understanding that, the vector r hat tells us that we're pointing in the direction from the origin to the point, and the scalar r tells us how far away the point is, just like how polar coordinates work. And when we combine these two, we get a vector r that is an arrow that starts at the origin and ends at the point that we're describing. And we can define another unit vector, theta hat, which we don't necessarily have to use when describing position, but which is helpful to have when describing changes in position. So theta hat is orthogonal, which means perpendicular, to r hat, and we define it as negative I hat sine theta plus j hat cosine theta. And what this means is, let's say I were to rotate the vector r counterclockwise around the x-axis. So the direction that I would push the tip of r hat, if I had my finger, I would put my finger underneath the vector r, and I would push it upwards, right? So that's the direction in which theta hat points, because if we go in the direction of theta hat, it means that we're increasing theta. So, I push r upwards, that means that I'm increasing theta from theta equals 0 to theta equals, something non-zero. And so, yeah, it's pretty simple to see if you take out your favorite graphing tool, Desmos, for example, and you plot out r hat and theta hat. It's very easy to see that r hat and theta hat are always perpendicular to each other. And yeah, while the position vector is always described in terms of r hat, any changes in the position vector that don't involve increasing or decreasing its length, but only changing in which direction it's pointing, involve motions in the direction of theta hat. And we will return to r hat and theta hat later in this course when we describe rotations. Right now, if you're kind of confused about the way this works, that's okay. but make sure that you have a solid understanding of their Cartesian basis, I hat, j hat, and k hat, which are much simpler than r hat and theta hat. And we can treat vectors as their own class of numbers, and as such we have some operations that we can perform on them. So I've defined two vectors here. We have u, which is equal to a times I hat plus b times j hat plus c times k hat, and v, which is equal to x times I hat plus y times j hat plus z times k hat. So first let's introduce the idea of scalar multiplication. So as I said earlier in this lecture, a scalar is a real number. It does not have direction, it only has magnitude. So let's say I take some scalar lambda, that's the strange looking symbol on the left side of the v right there. It's a Greek letter. Now if I wanted to multiply this scalar lambda by the vector v, then what I would do is I would multiply each of the components of v, x, y, and z, by lambda. So we have lambda times v is equal to lambda times x times I hat, plus lambda times y times j hat, plus lambda times z times k hat. So if you think about this, basically what we're doing is we're making each component longer by a factor of lambda, or we're lengthening the vector by a factor of lambda, and note that that does not change the direction of the vector at all. Now, I was speaking about length, and a way to find the length of the vector is through, the good old Pythagorean theorem. And we also call this the magnitude or the norm, and we represent it in a similar way that we would represent absolute value, with two vertical lines on each side, not one. And as in the Pythagorean theorem, where distance is equal to x squared plus y squared plus z squared, if we're taking the magnitude of a vector u, as we defined u, it's got an x component of a y component of b, and a z component of c, then the magnitude, which is kind of the geometric length of the vector if you think about it in three-dimensional space, is equal to the square root of a squared plus b squared plus c squared. Again, the same way that you would think about it with the Pythagorean theorem. And finally, we're going to define the dot product. This is a way of combining two vectors. And as you can see, u and v, they're both in boldface. That means that they're both vectors. And if we combine them with the dot product, then we get out a scalar, which is equal to each of their x components multiplied by each other, plus each of their y components multiplied by each other, plus each of their z components multiplied by each other. So ax plus by plus cz. And this definition may seem somewhat arbitrary to you right now, and it's not a very important definition at this point in the course, but we will bring it up later, as well as another way of combining vectors called a cross product. And this will be relevant later on in the course when we discuss work and when we discuss rotations. So finally we have the idea of a reference frame, and this is a very critical concept in not just Newtonian mechanics, but in special and general relativity as well. So basically the idea is that we have multiple ways to describe space, right? Like I can say, I have this coordinate system and you can have another coordinate system, and neither of us will agree on what our coordinate systems say. So we call that each of our frames. Now in physics, each frame consists of an origin and a coordinate axis that we use to describe space. For example, I'm here right now sitting in my chair talking at my laptop. Now, let's say I'm the origin of my own frame. Let's just ignore the fact that I'm a large person, and we'll pretend that I'm a point for now. I'm the origin of my own frame. If I look up, I'm looking up the z-axis of my frame. If I look towards my laptop, but just straight in front of me, let's call that the x-axis of my frame. And if I look to my right, let's say I'm looking down the y-axis of my frame. I can describe all of space, say where it is, by saying, if I look up and I walk up. If I fly up that much, and if I go forward that much, and if I go right that much, then I'm at some point, x, y, z. So that's a way I can define a frame. And you might be thinking, okay, yeah, this is just the same as what we've done back in geometry, back in algebra when we were plotting things out. Why is a frame special? So like I said, there are multiple ways to describe space. My little brother is outside right now. Let's say he's walking towards me. So he is the origin of his own frame, right? So the way he sees it, points have a different coordinate points have different coordinates from his perspective, right? And because he's walking towards me, the coordinates are changing. So the difference is that, let's say he's walking towards me. If I see him moving, he sees himself at rest. So that's the difference between our frames. And thinking about how frames move relative to each other, we can define an inertial frame and a non-inertial frame. Now, the definitions of these are somewhat convoluted, but let's just say that in an inertial frame, an object that has no forces acting on it is at rest, and we'll talk more about the concept of a force later. But all that's important to know is that if you're in empty space, that is an inertial frame. If you're on Earth, that's not really an inertial frame, but it basically is. And the thing about inertial frames is that they're always moving in constant linear motion relative to each other. So the reason for this is that, let's say a frame is accelerating, you know? I don't have my license yet, but let's say I decided to get behind the wheel of a car and press the accelerator button. Then, even though I'm at rest in my own frame, I have forces acting on me, right? I can feel that the chair behind me is pushing me, right? But I'm at rest. So that means I'm not in an inertial frame. I'm in a non-inertial frame. However, in an inertial frame, like I said earlier, if there are no forces on you, then you're either at rest or you're moving with constant velocity. And if you're at rest, then there are no forces acting on you. So we have another principle called Galilean relativity. And this says, I've provided a kind of hard to read definition here. If frame B is moving with velocity v with respect to frame A, then frame A is moving with velocity negative v with respect to frame B. So you'll notice that I've bolded the velocities v and negative v here. That just indicates that they're vectors, right? Because I need to say both how fast frame B is moving and in which direction it's moving. So again, let's take the example of me and my little brother. I am sitting in my chair, I am frame A, and I see frame B, which is my little brother, moving with some velocity with respect to me, right? So if my little brother were to look at me, which he is not, he would see me moving in the opposite direction at the same speed, right? Or if you think about it, if you're on the highway and you're driving in your car at 60 miles an hour and the guy next to you is speeding terribly, he's going at 80 miles an hour, then in your car you're at rest, right? So you see him moving at 20 miles an hour. Let's ignore the fact that you can see the surroundings. If you guys were in, a blank, dark room and you were moving at 60 miles an hour and you had no speedometer, you wouldn't know better. You'd see, okay, yeah, I'm at rest because I can't tell that I'm moving. And the guy next to me, he's moving 20 miles an hour faster than I am, so he's moving at 20 miles an hour. But the guy next to you, he wouldn't be able to tell that he's moving, right? Is something that we're going to use human physics, right? Again, in your own frame, you're always at rest. Every observer defines a frame, and in their frame, they are at rest. And at rest means that you're not moving. So, again, the car next to you, he doesn't see himself moving, but he sees you going 20 miles an hour slower than him, which he perceives to be negative 20 miles an hour. Or in other words, you're moving 20 miles an hour, but backwards. You're going backwards from his perspective. So yeah, that's the principle of Galilean relativity for you. And of course, this might seem like fairly arbitrary definitions and statements of obvious fact, but they are very important to understand when we move on to, for example, collisions or forces or other problems in which, changing frames is an absolutely invaluable tool for getting a different understanding of how the problem works. So yeah, that is the end of today's presentation, today's lecture. Thank you for watching. I will try to publish a problem set, and I'll see if I can set up an office hours if you have any questions. And yeah, again, thank you.